Okay, so thank you everyone for making it this morning or noon for you. It's a bit early here in Montreal, but I wanted to try to make it as early as possible to be able to accommodate the European customer base. Um, so today we're really going to tackle something a bit more niche in terms of on wafer load pull. We've talked about more broader topics like the introduction to load pull and some waveform engineering topics. So to do this today, we asked our partner MPI Corporation and Dr. Andre Rumantsev. Hopefully I did that not too bad, to help us out, on certain aspects of calibration, probing, and some deeper, technical topics that a lot of people, I think take for granted and don't appreciate the effort that needs to go into to getting good results. So it's going to be a two-session webinar where I'll cover some of my topics first, and then Andre will cover the second part. So let's just get started. So the agenda, again, we're going to go over, basic things at the beginning, just load pull setups, limitation of tuning ranges, typical on-wafer setup, and the typical on-wafer setups will cover like sub 6 gigahertz, the 5G, sub 6 gigahertz and millimeter wave is really popular now. So we'll take a look at those stuff, and even 110 gigahertz setup. And then Andre will pick up the puck there and cover different things, again, parts of calibration, S parameter measurements, and things like that in a more thorough way. So again, load pull setups. Okay, we've had a few webinars on this, so we've covered these topics a bit. So it's going to be a very quick overview. This is usually how things happen for me. I get a call from a customer or from MPI, and they say like, oh, we have this opportunity where we want to, put this great product of ours, our probe station, and they want to match it with one of your great products. And, at the end, we need to figure out how this big tuner can mate on a probe station like this. So yes, individually, these products are great and very popular, and, they're really, we're really proud of these, but the problem is to make these things to work seamlessly together is not as easy as it seems, It's bulky tuners, you have microscope, RF probes, DC pins. There's a lot that goes into it, and really have to take a lot of effort to do it right, and to basically keep the performance as is once you migrate from like a fixture measurement to non-wafer measurement. So I want to give a quick example. So this is more of a fixtured measurement, right? Where, here's one of our application engineers, Tim. This was probably 4 or 5 years ago. We were doing this demonstration in a hotel room. And as you can see, he's all excited. He's ready to go. Very simple setup. You have a table, you have a few longer cables, you could accommodate. Very simple setup. Fixtured measurement. Yes, there's some, expertise that needs to go into the fixturing of it, like transformation fixtures, biasing, things like that. But usually that's pretty simple way to connect and set up everything. Mechanically, everything, sets up seamlessly. The size of the tuner is not really a problem. This is what it looks like when you're not prepared and you go to an on-wafer, demo or a setup. And this is an example of when. So all these setups that are not good are basically setups that I was part of. So I could show them, and this is basically what I'm trying to show you is what not to do. So as you can see now, this setup, we're trying to set it up on the probe station, and you can see here, this is a mess. There's a right angle connector. It's not a low loss cable. There's all sorts of cables. We're using the tuner as the mouse pad. This was not poorly planned, and we're just trying to get some measurements done. But clearly, this is not the recipe for success. And you can look at even Nevin's face. You can see that he's not happy. This is going to be a difficult situation, right? So the last one example is this is a noise system. Again, there's some DC probes, 90-degree, probes, not easy to integrate. This is a small tuner, and even this takes a lot of time and effort to look into. So, this will give you, you look at this cable that's basically connecting from the tuner to the probe. It's awkward. It's bent. It's in a weird shape. This is not a recipe for success, right? So in the end, what are we looking for? We're looking for stable, repeatable contact. Okay, the tuner works well on itself, the probe station works well on itself, but if the tuner's moving and there's some vibration in the tuner, vibration in the cable, and you connect and it translates to the probe, it's going to be a problem. We're looking at micrometers here. You want the probe tip to land correctly on the pads on the device so that you could calibrate accurately, and that you can measure accurately. If you have a one pin that's in the air that's not landing right, or it's kind of landing too, or it's moving, there's oxidation, this is a nightmare. So this is something that takes some time, and integration on a probe station is a big thing. Okay, so when you get a brand new through, you're all excited, everything's clean, that it's a perfect start. This is what the pads or the probe marks of let's say you want to do S parameters, because the S parameter measurement, you're basically lifting the probes up and down, you're landing, you don't need to dig in too hard, and it's a measurement that doesn't need to sit there for a very long time. Load pull is a very different thing. You need to sit down on the probe on the substrate for a very long time. So here's an example of, like a poor calibration where the probe tips are actually moving on the input and on the output. So you see that we're slightly damaging the substrate at this point, and that will have an effect in the long term. Okay. So here, once, most of the time what we do is the source tuner, we do a bit of source tuning just to kind of get in the right area, but then we do a lot of load pull, and then we do a lot of movements, and then, it starts chewing up the through. So this is something that we see, unfortunately, on systems that, we're poorly managed and not necessarily well integrated. So a lot goes into, putting this so that the tuners are very close to the probe tips and allow to, greater tuning range, but also allow minimum vibration, right? So if somebody's attended the Introduction to Load Pull webinar we had, I have 2 slides. It's basically the introduction. So here, basically what we're trying to do is we're trying to control the A wave. So the wave that we're reflecting back to the device. So there's different ways of doing this. Either you do it with a passive tuner, you would do it with an active tuner where you're just injecting the A wave, or you could do a combination of both. Today, we're going to really focus on the passive version of it, okay? So again, we're focusing on this A wave. The DUT will generate the B wave, and then the load that we're going to be using will basically be reflecting that A wave, and that's what we're trying to control here. So again, for passive tuners, the way we do it is, we inject the B wave that goes through the tuner. This is when the tuner is initialized. So if we put the RF probe that's in the tuner and it's totally retracted, what happens is the B wave just goes through, and that's like a 50 ohm match. It's a very good match. So in other words, you're not tuning out on the outer rings of the Smith chart. You're basically tuning at 50 ohms. But as we bring the probe down, and you inject the same B wave, well now, depending on what position you are, you're reflecting that wave back, and that now you'll have a component in the A wave, and that's how you basically create, the impedances and control it over the Smith chart. Okay, so we'll talk about how we do this within the tuners here. So the big thing with passive tuners is the tuning range limitation. A passive tuner will not be able to go outside the Smith chart like an active system. So you're limited, at the tuner reference plane, you're limited, within the Smith chart. Now, as you add loss, add a cable, adapter, or probe, this will limit the tuning range, okay? So again, at the tuner reference plane, on the right, you see the gray area is basically covering most of the Smith chart. And you'll see, specifications on tuners at the tuner reference plane, they're very high. They could be high frequency, low frequency. We have these waveguide tuners that go up to 110. They are, extremely high tuning range. But unfortunately, you still need to connect it to a device. So even if you have 30 to 1, 50 to 1, VSWR, the tuning range, that doesn't mean much until you actually put something to connect to the device, right? So, the DUT reference plane, or, it could be a cable reference plane, but basically, our DUT reference plane will change depending on how we connect the tuner to the device. And basically what we're doing here is we're adding some electrical length, so a cable or probe between the tuner and the device. So what will that do? as we increase the electrical length between the tuner and the device, we increase the insertion loss. So we add insertion loss, therefore, limiting or, diminishing the tuning range of the tuner. So again, as we, you've seen here now that the tuning range is less because we moved away from the tuner reference plane. As I move away further, the tuning range goes even less, right? So the further, the longer the cable, the more probes, the more adapters, the bias T, couplers, whatever you put in there, the more you add, the less tuning range you'll get. Okay, so this is an obvious thing. So now people will say, okay, so I just need to have like a very low loss cable and a low loss probe, and it should be pretty straightforward. But there's more to it than that. So here we'll give an example, the T50 probe, but we use quite a bit. We love this kind of probe. It's very durable. For load pull, we do multiple contacts. We do measurements for a very long time. So one of the main things is durability, but then there's insertion loss. So again, if you look at insertion loss here, this is the tuning range again of a tuner, but if we look at just past 30 gigahertz, the insertion loss is about 0.4 dB. So we know that that's going to reduce the tuning range a bit, right? So now I'm exaggerating a bit, but just to kind of explain just the concept. So basically, the insertion loss will reduce the radius of this tuning range. Okay, that's the first thing you need to look in. You look at insertion loss as low as possible. That's a very important thing. The next important thing that a lot of people take for granted is the return loss. So you see here the center point of this tuning range is at 50 ohms, okay? But now depending on what frequency, if you look at the lower plot, that's the return loss of the probe. So, you can see here that this probe is really good, across the entire frequency range below 20 dB, but 20 dB is still 0.1 gamma. So, at certain frequencies, let's say we look at, a specific frequency here, like around 33 gigahertz, you can see that we're at minus 20 dB. So how does that translate into the tuning range? People will say, no, it's only insertion loss that's going to reduce it. But what happens is now the center is going to be offsetted. So instead of being 50 ohm, it's going to be slightly offsetted to 0.1 at a certain phase. And that's something you cannot correct for with the tuner. So what's going to happen now is that tuning range circle is going to be shifted in a certain area of the Smith chart. And now you can't compensate. If you're lucky and your impedance is on the right side or it's going north, then you're fine. Then that's actually helping you. In this case, it's acting a bit like a pre-match. But in my experience, most of the time, the probes is in the wrong area, especially at the low frequency, because at low frequency, it doesn't turn as quickly, and the phase is, it's depending on what position you are. Usually, you're going to be on the right side, and the impedances are going to be on the left side. At 20, 30, 40 gigahertz, well, then you could get different responses, and sometimes it could be on the left side, sometimes it could be on the right side. It really depends in this case. But that's something to look into. A lot of people underestimate or don't appreciate the return loss aspect of a probe when choosing a probe. Okay, so again, what affects tuning range? We talked about insertion loss. So this is the typical vector load pull setup where you have your tuner, a coupler, a cable, and a probe. Okay, so what happens here is we'll basically, look at the tuner, the tuning range of the tuner reference plane is very high, but again, as we move away from this reference plane, the tuning range is reducing. We'll see that before. So now you've reduced it because of the coupler. So now you have to add a cable. Once you've added the cable, you're reducing it again. Again, I'm exaggerating a bit the phenomenon, but if you're measuring at 30 gigahertz, you will get these kind of reduced tuning ranges. And again, the probe will also add that. And again, finally, you'll add something even at the end. You'll add a termination. So you'll add a bias T. You can have an isolator. You can have something on the output of the tuner. And that will also shift the tuner in the tuning range on a certain side. So you can see that in this case now I had great tuning range at the tuner reference plane, but on certain areas of the Smith chart, I don't really get that great of a tuning range. So these are things that really need to be looked at seriously when you do on wafer load pull, okay? Phase stable cable, so, I have people that say, well, I'll just put a very phase stable cable, I shouldn't worry about it. Or some people say, no, I just want the shortest cable as possible. But here I took an example of Gore. So Gore has, very, very good cables. We use them a lot, and a lot of our customers have them. And but I wanted to look a bit on the specs. So here, if you look at the lower line here, there's some specifications, and the typical phase stability is what we're really looking for. We're looking to optimize. So I'm not going to talk about tuner calibration, but really quickly, when you calibrate the tuner, obviously you do a coax calibration, and then you want the cables to be very stable. Then you connect it to the tuner. So you're looking for this, plus or minus 2 degrees of stability. Okay. But if you're not careful and you use like this OM version of cable, now you can have, plus or minus 15 degrees. So plus or minus 2 degrees at like 18 gigahertz, that's still decent, but that's still not nothing. But plus or minus 15, you're talking about like 20-30 degrees. So you can be 20-30 degrees off of your impedance. That's a huge phase shift if you're not careful. Now, okay, there's a caveat. It says when the cable is wrapped 360 degrees, and in our case in low pole, we never wrap it around 360 degrees, but it just gives you like the margin of error you could face if you're not careful. So how does that translate into tuner calibration and impedance presentation? So here's an example of a tuner with like a gray cable, like a very, this is a cable that we're using, and we're just calibrating the tuner at this reference plane. So somebody that's used a tuner before, you have basically these impedance points across the Smith chart. So when you calibrate the tuner, you create this table of S parameters, and you associate these X, Y positions to the tuner to these set of S parameters, right? So when you have the tuner calibrated and you use it after, so this calibration needs to be very accurate and cannot change. So in other words, when I go to a certain impedance point or a different XY position in the tuner, I assume that this point is going to be good and it won't change. So the problem is if I have a cable, so now if I change this cable from a very straight, rigid cable and I put like this, flexible cable, or I start bending the cable, what I can see is like, the points have shifted. So this is like a 2 degree phase shift. So now you can see the red crosses are off what the original points were. So now when you start measuring, your impedance is off 2%. So, this, depending on how accurate you want and, how far you can push this, but now, and this could be seen when you do a match verification later. So then when you start shifting these points, well, you're trying to set a certain impedance, but you're actually somewhere else. So that's 2%. Now, if I bend it a bit more, and trust me, we've bent a lot of cables through the years. And so now this is a 15 degrees phase shift. Okay. So now you're totally off. Now you're like literally, 15 degrees off of your initial point. So near 50 ohms, you don't seem to be so far off. It doesn't seem to be so bad. You're still 15 degrees off, but the magnitude is not as much. So, but if you're looking, at a very small impedance, you have a very, very big impedance shift, and this is going to be a problem in the long run. So at sub 6 gigahertz, it's, I would say it's less of a problem because, again, at low frequency, the wavelength is longer, so the electrical length is shorter, and it's less of a problem. But here's an example of a system here. This is a 0.8 to 8, and so there's two flavors of this tuner, and you can see on the top here there's a 0.8 to 18 gigahertz tuner, and there's that one is probably like a 10 to 26 gigahertz tuner. But basically what it's showing, there's these rigid air lines. So some customers, say, I don't want the cable or the impedance to change whatsoever, so I need a rigid air line between the tuner and the probe tip, even if it's at low frequency. So to accommodate this, you need to move the tuner basically. Now you can't just use a small positioner to move the probe, because even when you do move that, even if the tuner is fixed and you actually move the probe, well, there is, even if it's micrometers, you're still moving a bit. You do a calibration, you need to do a TRL calibration, so you need to open it up for a delay line. So you're moving, the device has a different, pad distance. So, you're still moving that probe tip a bit. And the more you move it, the more it will introduce in uncertainty and phase error. So here's an example again on in the middle here and at the bottom, where the tuner is actually residing directly on the positioner. So, but we'll show that more into detail after. Okay, so again, here this is the full system. So again, the we wanted the best tuning range as possible. So you see both tuners have rigid air lines that go directly from the tuner to the probe tip. So you connect the probe tip directly to the tuner, and then you use these positioners. So there's a more zoomed in version here. So you can see here there's 4 knobs. So there's an XYZ position and there's a theta position as well. So one of the not problems, but one of the concerns with a rigid systems like this is when you sit down the tuner and you fix the probe, it's not going to be necessarily planarized perfectly. So you need to have a theta adjustment to actually move the tuner. So here, as an example, the tuner, this is a heavy tuner, this is over 50 pounds, is sitting on this heavy duty positioner where you can move it XYZ and theta as well, and you get the best of both worlds. You get the best tuning range, and you basically get the phase, very stable, rigid line that doesn't move and provides the most accurate measurement. Okay, so at low frequency, like I said, the tuners are big, wavelengths are long, so it's there is a bit of a margin for error. But as you go higher in frequency, customers say, well, this cable, I don't care what cable, it could be as good as you want, 30 gigahertz, as soon as I move anything, I get a phase error and then my calibration's off, my match verification's off. So how can I do this? So I remember 4 years ago, we had an internal meeting where we said, well, it's easy, just eliminate the cable. But as you've seen, the tuners are big, and it's not simple. It's not that simple. So we can't just flip the tuner around and say, okay, connect like that. The tuner is slightly bulky. There's a microscope. There's some DC. There's all sorts of things that were going to kind of conflict here. So removing the cable was not that simple. And here's our first attempt at the Delta tuner. So clearly, we were trying to get the tuner very close, and then we had a small cable to get the best tuning range, and we had this very, precise book, and we're just trying to get the tuner as close as possible. But clearly, this is not a feasible solution. So we had to find a way to really, reduce the size of the mechanics inside the tuner to provide, accurate results and connect directly to the probe tip. So here's a snapshot of the traditional tuner on the right. Again, this, I would say 4 or 5 years ago, we were very proud of this tuner. This is a 10-67 2-frequency tuner and had a rigid airline. But again, you see that the tuning range, the tuning probe is actually at the window plane. So even if it's a very low loss rigid airline, the tuning range is reduced significantly. Okay, so customers needed, higher tuning range. They needed, 0.8 gamma at high frequencies. They couldn't deal with like 0.7, 0.6 gamma. They needed more. So on the left, you can see this is the same tuner. This is the fundamental version on the left, but it's the same size as the harmonic tuners basically. And as you can see now, the tuning probe is, an inch away from the probe. So that makes the tuning range drastically higher. So now in this case, we've reduced the cable, we reduced the need for a coupler as well. So it's really, really, the best tuning range performance you can get out of a passive tuner for on-wafer performance. Okay. So what does it look like for millimeter wave? So we've integrated a lot of, 10-67 to up to 110. The top picture is probably our most popular one that we've had just through the past 2-3 years, from 10 to 50, 10 to 67. On the right, you have, even 28 to 110 gigahertz. So, we have customers now that want to push, that do some advanced waveform engineering, like not only with one frequency tuning, they want to do like multiple frequency tuning, look at the waveforms and see how, when you move the harmonics on both the input and output, how the waveforms change and how to design amplifiers using that kind of technology. So we were able to provide solutions like this from the 28 to 110 with multiple frequency tuning on wafer, very well integrated with MPI with their positioners as well. And on the right, you also see the key side head. It's just peeking out there, so it's very well integrated. You get the best performance, super accurate, very phase stable, and reliable contact. Okay, here's probably one of the most advanced load pull setups in the world. This is again roughly 24, maybe 28 gigahertz to 110 gigahertz. This is a fully vector load pull setup. Probably one of its kind in the world. You could do, again, fundamental, pre-matching high VSWR. You could do fundamental from like 28 to 110 gigahertz. You could do some waveform engineering. So you see that the positioners here move the entire test set. That's actually an external test set in this case. And, it's a very advanced system. It's well integrated with the microscope. It actually goes between, and it connects directly to the probe tip. So this is just an example, another example here. Okay. So again, I won't go too deep in here. I want to give Andre a bit of time here. We're already 30 minutes into it, but basically, there's people use in different ways. There's the typical scalar setup where, again, you have your two tuners that are connected there. You have an input block where you could basically just calibrate out the loss of the input block and the coupling path of the coupler, and that's how you can de-embed back to the probe tip. Same thing on the output. There's different paths you can take, either just an output path from the bias T to the coupler, or if you're using a spectrum analyzer to measure harmonic power and whatnot, you can also couple that. So how do we calibrate this tuners in this case? Because people are more familiar with the low frequency, where in the low frequency you could actually calibrate the tuners separately. And then, because let's say the low frequency tuners are a bit bulkier, so some people might just say, no, I just want to calibrate there, but I'm going to add a cable from the tuner to the probe tip, and if I want to swap out the cable from time to time, I can do that, and I don't affect tuner calibration. But at high frequency, you can't really do that. So what we do is we have an in situ calibration. So what we do is we do a coax calibration of the cables, and then you connect it to the tuner, and then we do a TRL measurement. So the goal there is to basically de-embed the losses of the input tuner and the output tuner, and which we call connector A, connector B. And basically when we calibrate the low tuner, we can de-embed the source tuner and vice versa. And this is how we're able to do a calibration with the tuners, in situ, already connected to the probe tips. So, and then on the left, again, the last step is to do a power calibration. So what we do is we have, again, the connector B there that we basically de-embed, and we could do a power calibration at the DUT reference plane by de-embedding the cone B and measuring with the power meter on the right there. And on the right, you basically have the full vector receiver set up with the couplers and directly connected to the receivers of the PNAX. So this is a fully vector corrected load pull system. Again, we have multiple bands from like 10 to 67. We're actually, for IMS, we were going to promote also a new band. You'll be here for that, but basically the goal was to go lower in frequency. So stay tuned for more information on that. And again, the ultimate goal here is what is a match verification. So in load pull, the way to verify the system is pretty straightforward. So, we do what we call a wave cal or a vector cal after we do the tuner cal, and we need to be able to tune the tuners on the source and the load at match conjugate impedances and get a power gain and transducer gain that is very low. So here you can see that the gamma that we're presenting from 0 to 0.8. So I think this is probably, this is Suhas that probably did this measurement. This is probably like at 28, 30 gigahertz. So what we're doing is we're doing load pull on the source. So we're changing the source impedance and the load impedance, and we're measuring what the power gain and transducer gain is for all those impedances. And this needs to be very low. So I remember historically, so I would see engineers would have 0.5 gamma and a match verification of 0.7, and they were happy with that. Here we're, and these are actually one of the first, measurements we're doing. Now we've been kind of tweaking some calibrations and optimizing a few things, but this is the kind of match verification we should expect at a minimum. So here the worst case is about 0.2 dB at 0.8 gamma. So, so now you know that when you get performances like that, your S parameter measurements are good, your tuner calibrations are good, and all the de-embedding is right. And this is the kind of performance you should expect from a system like this. So now I guess I'll hand it off to Andre here. So I guess Suhas, you can, let me just stop sharing here. Andre, you still there, or did I lose you?
Oh, I'm here.
Oh, good, good.
So very, very nice start. All right, can you hear me well?
Yep, perfect.
Very well. Let me take from here, and the last part of our webinar, we will be talking about wafer level calibration, what is the specific problems and available solutions today. Before I start, I would like to drag your attention to probably a very simple concept, but still sometimes not really well understood in the practice. And in fact, all the RF measurements that we do are the results of the mathematical data post-processing, which means that before we see a parameter of our device under test, we need to do several measurements in advance, like calibrate our system and correct calibration systematic measurement errors, and define them and embed our device under test from the measurement setup, which means that the data consistency and data repeatability, where we were talking about this already, and Vince pointed a couple of times, becomes very, very important. So the key success factor when we do on-wafer measurements is repeatability and reproducibility of our data. And the contributing factors to this success are, first of all, the RF probes, of course. This is a physical interface to our device under test, which connects the measurement setup to the DUT terminals. Then also system mechanical characteristics. If you have a good probes but the loose system and you cannot position the probe at the same point of contact every time you need to measure your device under test, this will significantly reduce the accuracy of your measurements and accuracy of your calibration. And the system positioning accuracy is usually given by the system design, the optical system resolution, the stability of the positioners, the stability of the probe arms, cables you use. This is all in total. It sounds very simple, but there is a lot of expertise and understanding behind the system, which provides you with a stable and repeatable data. So then calibration, the accuracy of planar calibration standards becomes an influencing factor. So with the frequency, the pre-knowledge of calibration standards changes, and we may have a good, stable calibration results very well to understand at the low frequencies, and it becomes very difficult to understand at the higher frequencies. And calibration algorithms. We have multiple calibration algorithms developed today, and all of them have their advantages and disadvantages. Why do we have so many calibration algorithms? First of all, it's easy way to look at the calibration algorithms is that to split them into major groups. One of them is so-called straight calibration methods, which do not allow us any freedom in calibration standard electrical models. So it's just direct calibration like SOLT, SOL, or quick SLT, where we need to know electrical characteristics of every calibration standard. Advanced calibration method, in contrast to the first group, it gives us some more freedom in electrical characteristics of one or another calibration standard. And in this case, the real art and the key success for the application people is to choose the right calibration algorithm, which is less sensitive to a particular set of problems that we have on our measurement setup, and shows the best calibration advantage because it addresses the problems in the best way. When we do the system calibration for load pull measurements, as Vince already mentioned, we have multiple types of the calibration we have to execute and go through. And this is the calibration to the, usually to the cable end, which we typically use to calibrate and characterize the impedance tuners. And then also, this is the in-situ cal or on-wafer calibration, which we need to do to move the reference plane to the probe tip end. When we do cable end calibration or calibrate our system for the coaxial measurements, we use a set of calibration kit. It's well-defined calibration standards. We know the electrical characteristics defined by the vendor. The standards is easy to operate. We connect them to the end of the cable, and we have very reliable calibration results, in particular when we use the top ranges. When we move to the wafer level measurements, actually the situation changes completely. In one of my previous presentations, I mentioned that you basically fall into the rabbit holes like in Alice, and everything flips upside down, and I still have the same feeling when we do the on-wafer cal. Now, this problem was first identified for the engineers when they start doing the first repeatable measurements of a planar devices all the way back to 1975. Hewlett Packard did the first pioneer in this area and did the first wafer measurements up to 3 gigahertz frequency range. Then the technology was rapidly developed, and the first commercially available probes became available late 80s. So over 40 years development of the wafer level measurements, the technology made significant, actually tremendous progress. And today we are able to do the wafer level measurements and the frequencies beyond 1 terahertz. This is really amazing. The set of the challenges and the problems that we need to deal with when we do on-wafer measurements also changed with the technology development of the probes. Some of them became irrelevant or less relevant because we found the solutions for them. Some others became more relevant today, more dominant, and engineers are still working on the solutions with them. Here I will give you several examples of them, and we will go through one by one. For instance, like a probe contact visibility and repeatability of the measurement data related with bad visibility of the probes. That was relevant for the first generation of the wafer level probes, and for today's generation becomes significantly less relevant, and for some probes even irrelevant at all. Asymmetry of the measurement standards. When we do wafer level measurement, we usually measure port 1 and port 2 standards at once, and standards are represented by 2 physical elements like pair open, pair of short, and pair of loads. And if you cannot position the probes on the standard accurately, your standard electrical characteristic become asymmetrical. That was a big problem for beginning of the on-wafer measurement history, and today it becomes relevant because engineers found a very good solution. Impedance of the planar calibration standards. First, to characterize the equivalent impedance of the first coplanar standards was very difficult. People had difficulty to understand what is the equivalent impedance of the load, how to measure characteristic impedance of transmission line. But today we believe that we know how to do it. There is a lot of work already completed, and its problem becomes less relevant. What we deal with today as a set of the problems is how to debug and how to get rid of device infrastructure like pads and interconnects. It was less relevant in the past because devices were large and measurements frequency was below a few gigahertz. But today, for sub-terahertz measurements, it becomes a very big problem. Device and the test is far away from the probe tip. And also today, because we have a laboratory spread over the globe, and we ship the wafers back and forth, defining the measurement, understanding the measurement uncertainty, and defining measurement uncertainty for wafer level measurements becomes a very important problem, and specifically relevant when we do wafer level measurements at millimeter wave frequencies. So let me review these problems one by one. Probe contact repeatability and visibility. For the first generation of wafer probes commercially available, like WPH for cascade microtech, it was very hard to define the electrical point of contacts because it was basically hidden by the probe structure. So which means that achieving reliable and repeatable contact was purely on the operator's shoulders. So experienced operators could get reliable measurements, unexperienced operators couldn't get reliable and repeatable measurements out of the measurement system. And this fact caused another problem like an asymmetry and electrical characteristics of the calibration standards. With the new generation of wafer probes, as an example showed here, when we have a 3D structure of the contact tips, the point of contact is as same visible as for DC measurements. So you can clearly see the point of electrical contact under the microscope, and you can locate the probe and the desired position of the contact pad, and do it at any time you want to probe a device on the test or you touch down the calibration substrate. So it's alignment of the probe is very easy, and thus repeatable and reproducible results are very easy to achieve. In fact, for the new generation of the probes, you even don't need to use the alignment structures. So repeatability of the contact is another point, another important mechanical characteristic of RF probes, in particular when we do load pull measurements, because as Vince already mentioned, we need to stay in contact for the long time, and because the tuner is operating, changing the load impedance and source impedance. So the capability of the probe to provide stable contact resistance over the long time when being in contact, and on a very difficult material, patternization material such as aluminum, is a key characteristic for the load pull measurements. And for the probes which have nickel alloy tips, it's possible to achieve very stable contact resistance over the long time in contact, and also over the number of touchdowns. Like what you can see here is the contact resistance is exactly the same, up to 1 million touchdowns. Asymmetry of the standard impedances. We talked about it previously. So basically, the asymmetry of the impedance of the pairs standards is the root source for that is the probe placement problem. If we fix the probe placement problem, then actually the asymmetry of the standard impedances goes away. For the first solution, because it was not possible to predict the contact position and of the first probes, engineers came up with a very smart idea. They did a lot of experiments, and they realized that actually asymmetry of the load standard becomes more important, because the load defines the reference impedance of our calibration. If loads is asymmetrical and have different load impedance port 1 and port 2, my accuracy of the calibration significantly reduces. Open and short asymmetry is still important, but maybe less important than the asymmetry of the load. And that is why they introduced the LRM calibration routine, which measures only one load and at the same time measures the pair of the open and the short. Good solution for the first measurements at the low frequencies, but still didn't answer the question of what to do with the asymmetry of the open and short standard, as well as how to measure accurately of the second network analyzer port, which was not calibrated using the load standard. And it's very good to know that with the new probe technologies and with the new systems which provide a very accurate probe positioning, actually this problem does not really exist any longer. Impedance of coplanar standards, it's another problem we mentioned. What we can see here on this graph is where the frequency increase, it becomes very difficult to provide an accurate model which captures characteristics of our open, short, and load standards at the higher frequencies. Here we look at the phase of the open and short standard accurately measured and compared with the traditional models that we use for the open and short, such as parallel capacitance and serial inductor. What we can see is that this model apply very well up to roughly 40 gigahertz, and beyond 40 gigahertz, they actually fail, which means that the standard the calibration methods which require accurate models for the open and short will fail as well, such as an SOLT. And here is a very interesting example of measurements of a coplanar waveguide line embedded on the wafer after the probe tip calibration corrected by SOLT up to 110 gigahertz with an accurate model of open, short, and load, and inaccurate model, just a standard model provided by the vendor. What we can see here is that if we do some additional exercises and characterize the standard open and short and load accurately, we can significantly increase the accuracy of the SOLT, even SOLT calibration up to, and push it up to 110 gigahertz. However, this is not always practical, and that is why engineers prefer to use the methods which are less sensitive to electrical characteristics of standards like an open and short and millimeter wave frequencies, such as LRM, TRL, LRM, TMR, TMRR. R stays for the open and short, which do not really need to be modeled accurately. So with the frequency increase, we have to do a little bit more than just the probe tip calibration. What you can see here on the slide is that when we use the probe tip calibration standards, our reference plane of our measurements is shifted to the probe tip. But our device under test is actually located far from the probe tip. And this picture gives us a very good comparison of real geometrical sizes for device under test. So where you can see the contact pads are much, much larger than the device under test itself. And the probe tip is not just the only step that we need to exercise. We need to do some extra steps like pad embedding routines. So, and shift the reference plane down to the device under test terminals. So from the probe from the probe tip and get rid of the impact of the device contact pads, as well as the via stack and other device under test infrastructure. So these algorithms, the embedding becomes very difficult to execute at the frequencies beyond 20 gigahertz. Industry conventionally uses an open and short de-embedding, which captures device under test infrastructure environment pretty accurately, but only up to the 20 gigahertz. If we need to verify extracted models, model parameters at the frequencies beyond 20 gigahertz, it becomes very, very challenging. So we need to use either advanced embedding methods, which require multiple steps, 5 or 7 embedding steps are available today, but they are really impractical. So the alternative way is to move from the probe tip calibration and the bad calibration elements on the wafer. So there's a custom on wafer calibration standards, and that shows actually very good calibration accuracy and measurement accuracy results. And this is the way to go. Different calibration methods are available, multi-line TRL for much higher frequencies, which is actually frequency unlimited, or if customers prefer, engineers prefer to use the probe tip calibration, this is through mass reflect or through mass reflect. Why through mass reflect or through mass reflect calibration algorithms are more preferable for the wafer level measurements? The first of all is because they do measure both load standards, port 1 and port 2 load, independently from each other, so the system is fully calibrated with the loads. And asymmetry of the load is allowed. This is a typical case when we make on-wafer calibration standards, when you have one stock parasitic of the stock on the port 1 and another parasitic of the stock via stock on the port 2. So basically the custom-made load is asymmetrical. Arbitrary impedances models are also allowed, so the load can be an arbitrary impedance element with even the load resistance port 1, port 2 different from each other, which typically corresponds to on-wafer calibration, custom calibration standards. So this algorithm is on-wafer ready. It has an additional advantage versus already known transfer through mass reflect algorithm. In fact, this algorithm has an extra reflect element. So you can measure both opens and both shorts. It adds an additional information redundancy on the algorithm, so the algorithm itself becomes more robust to the errors and improves consistency and reproducibility of the measurements. So next slide shows a comparison of conventional wafer level calibration routines like LRM, LRM, and TMRR in terms of the standards which are used. So through load port 1, load port 2, short port 1, short port 2, open port 1, open port 2. What we can see here is that through mass reflect use all possible standards for the additional redundancy of the measurements. By using 2 opens and 2 short standard, it's the best accuracy for when measuring highly reflected devices located in the both edges of the Smith chart, left and right. And by using the 2 load standard, we have the best accuracy for measuring well-matched devices like transmission lines or power amplifiers. With the frequency increase beyond and reaches millimeter, 7 millimeter wave ranges, we have actually a couple of other problems that we need to deal with. And in particular, this is the multimode propagation and the coupler waveguide structures, like a traditional calibration substrate, supports higher elder modes in the coupler waveguide, the transmission lines and standards if rest on the metal chuck. This is the picture shows us the electromagnetic wave structure at 110 gigahertz when the calibration substrate is placed on the metal chuck. What you can see here is that the waves are completely corrected because these are they are the result of the superposition of different modes, and higher modes are not desired for the calibration. Yeah. So this problem became the engineers became aware of this problem already at the measurements of 20 and 40 gigahertz, and the solution that engineers used previously was to isolate the calibration substrate from the impact of the metal chuck, so by adding an absorber layer in between. So this solution works pretty well up to roughly 50 gigahertz, but what you can see here with the frequency increase, absorber changes the characteristic impedance of the transmission line and increases the imaginary part of the transmission line. Basically what happens is that at the millimeter wave frequencies, we end up with a calibration reference impedance of a complex nature. And this is not what we actually want to do. The alternative approach is not to isolate the calibration substrate from the impact of the chuck, but to make the chuck itself from the matched material, the ceramic, which has the same dielectric constant as the calibration substrate. The first experiments, which were done back to 2008, proved that this concept actually works very well. And the main idea is that not to absorb the electromagnetic waves, but just let them dissipate into the auxiliary chuck and make it infinite of size versus the geometry of calibration substrate. And this idea was already proven by the Planer-Cal Industrial Consortium of European metrologists and engineers. If we want to do the accurate calibration of using coplanar structures at frequencies beyond 50 GHz, it's better to look at the material properties of the main chuck and the calibration and auxiliary side of the chuck. So another probably what happens is with the frequency increase is that it becomes very difficult to define equivalent impedance of planar calibration standard when it is located at the probe tip. Why it is so? Because the probe tip is the discontinuity point where electromagnetic waves are not formed properly. And it's always very difficult if you have a superposition of electromagnetic waves to define the equivalent impedance of the standard. To which mode do you define it? So we actually don't know. And what you can see on this graph is that the coplanar waveguide line mode is well formed only at a distance far from the transition point. This graph shows as a result of extracting load inductance out of the planar load, the probe tip load standard at the frequencies beyond 110 GHz. What you can see is that actually equivalent inductance of the load is not constant, and it varies from frequency point to frequency point, and there are several ranges where it varies really drastically, and we have the error up to actually 95%, which means that if we use this standard and we use this model, we end up with a very large error of our probe tip calibration. The possible solution for this problem is that they use the standard which are located far away from the transition point, which means that SOLT, SOLR, LRM, LRM methods are probably not desired when using the probe tip calibration standards and frequencies, millimeter wave frequencies. So either using the offset calibration standards, or what is the always better way is just simply go directly to the old wafer calibration standards, where your probe and transition point is far away from the physical location of the standard, and the standards are very close to the device and the test terminals. And the bonus you can have with this approach is that you get rid of the parasitics of your device and the test infrastructure. How to address the problem of the metrological level calibration accuracy, and as well as how to calculate and propagate uncertainties of your probe tip calibration. It's possible to do when we use calibration algorithms and calibration software developed by metrologists. One of them is statistical free software package developed by National Institutes of Standards and Technologies, available for everyone. The only limitation here is that you need to be a metrology expert to know how to operate the software, and to know how to set it up and use it for the calibration. And also you cannot connect it directly to the network analyzer. This is the tool which was developed for the data post-processing. So you cannot calibrate your lab setup and do S-parameter load per measurements with this type of the calibration. We suggest to use Calibre calibration software, which is also free of charge, free downloadable from the MPI web page. It connects this statistical calibration engine with the graphical user interface of Calibria, and makes the very complicated calibration routine very easy to use and implement in the daily calibration practices. And last but not least, this is the online calibration, which means that Calibria measures the S parameters of calibration standards, and also once the error terms are calculated by statistical, Calibria sends them back to the network analyzer. So you can calibrate the entire setup for your live measurements, just operating one software graphical user interface. The last slide is just demonstration what is possible to do using calibrated statistical calibration. Here is the measurements of the LNA, the frequency range from 220 up to 340 gigahertz on the way. At the Wafer, this is the LNA from Wafer in Freiburg, very, very good technology. And what we can see here is that we were able to characterize not only the gain of this LNA, but also to estimate the confidence interval, which makes the transfer of the measurement results from one setup to another setup much, much easier. Yeah, so, and this is all possible to do just with one software, Calibria and NIST statistical. We have an application note dedicated to this topic. Feel free to go to the MPI webpage and download this application note. And this is my last slide. It looks like pretty good in time. Instead of the conclusion, I wanted to share with you a table which may help you to make the right choice of the calibration method, depending on what you exactly do and what is your ultimate goal. So here you have a list of the popular calibration methods applicable for the wafer level system calibration, and different application scenario that like adaptive calibration, on-wafer calibration with the custom standards, measurements of the millimeter wave frequencies, measurements sub-terahertz frequencies, when we do the high refractive device characterization, or when we do the round device characterization. And the check marks help you to understand advantages or limiting factors of each of the calibration method. So thank you very much. This is all about the calibration I wanted to share with you today.